Hello, we have a multi-component steady-state gaseous diffusion in a Stefan tube. In this problem, we're trying to solve for the molar fluxes of acetone and methanol. We are giving the initial conditions for the mole fractions for Y1 and Y2. We're given delta, the tube length, the pressure and temperature, and the first thing I did was draw a picture. I think when approaching a problem, the best thing to do is draw a picture and see what's going on. At the liquid interface, we have acetone and methanol. At the screen at the top, we have air flowing through at a high velocity. And it's at the liquid interface, it's ranging from Z equals 0 to Z equals delta. The first thing we need to do is write the Stefan-Maxwell relation for the mole fraction of Y1 and Y2. The derivative of the mole fraction of component 1 with respect to Z is equal to the mole fraction multiplied by the molar flux minus the molar flux multiplied by the mole fraction of component 2. And then this is going to be all divided by the concentration and the Maxwell-Stefan coefficient. We're going to do the same thing for the right side. It's going to be y1 and 3 minus y3 and 1. We're going to write the Maxwell-Stefan relation for dy2 as well, since we're already at it. And this is going to be y2 and 3 minus y3 and 2, 3. So we have two first-order differential equations, and we need to make guesses. We need to make guesses for n1 and n2, and we can't just make any guess. So what we're going to do is we're going to make a new term, and this new term is going to be called eta. It's going to be z divided by delta. Eta is from anywhere in this tube length from here to here. And it's going to be dimensionless with the order of magnitude of 1, which makes the problem a lot easier when we're trying to solve. So the first thing we're going to do is we're going to apply the chain rule to dy1 dz. And we get dy1 with respect to eta multiplied by d eta divided by dz. As we can see, d eta divided by dz, and looking at this relation, we can see that that's also 1 over delta. So we're going to do dy1 divided by d eta multiplied 1 over delta. Now we're going to multiply this by the right-hand side. So we have dy1 over delta d eta and we're going to multiply both sides by delta. And by multiplying both sides by delta, we can cross out this delta term. And we can get the relation for dy1 over d eta. So we can find the order of magnitude for n1 and n2. We also know that n3 is air. And since n3 is air and it can't get into the liquid phase, that's equal to 0. And we know that y1 is 1 minus y3 is 1 minus y1 minus y2, because the sum of the mole fractions must equal 1. So we are then left, so we then know that the order of magnitude of the mole fractions is equal to 1, and the order of magnitude of eta is equal to 1. Because we know that that's equal to 1, we know the order of magnitude is equal to 1. So for the right-hand side, we have to get an order of magnitude of 1, because we're trying to find the molar fluxes of acetone and methanol. So we're going to write dy1 over d eta. We're going to say that's approximately y1 we know the concentration is also equal to the pressure divided by RT. And we know that this is also a gas. We know that the Stefan Maxwell coefficient, we know that this is a gas. And since it's a gas, that's approximately equal to 10 to the minus fifth. We know that the pressure is also equal to 10 to the fifth. We know that R 8.3 times the temperature, which was 325, that's approximately equal to 10 to the third. And that's also equal to 10 to the minus 3. And we know the mole fraction of y1 and y2 is 1. The order of magnitude for y1 and y2 is 1. We know this one is 1. We know this is approximately 10 to the minus third. This is approximately 10 to the minus third. 10 minus third. We get 1 is approximately equal to 1. And from that, we're able to find that the molar flux of N1 and N2 by a means of scaling is approximately 10 to the minus third.